just picking up with what we have had with inequalities, and we have just with the remaining portions of what we have for section 2.6, and looking into rational inequalities. Now we have a given function where we have x plus 4 over x minus 1, and looking at the four inequalities that will be brought up in the case of number 60. And we have for this particular function, if we go ahead and determine the zeros in terms of being able to set up our table, so we have two variable expressions in the ratio, where we have x plus 4 in the numerator, and then we have for the zero of the numerator, for x plus 4 equal to 0, we're going to have that x is equal to negative 4. And for what we have in the denominator, we have the x minus 1 is equal to 0. Where we have that x is equal to 1. And again, just setting things up. So again, we have, once again, we have the r of x is equal to x plus 4 over x minus 1. And now for the zeros of r of x, first, we have negative 4. And I'm going to use a little bit of shorthand. Now for negative 4, this comes from the numerator, and negative 4 will make the ratio equal to 0, like negative 4 plus 4 is 0 over negative 4 minus 1. 0 over negative 5 is equal to 0. And what I mean by shorthand, I'm going to say negative 4 ITD, and that's shorthand for in the domain. Now for what I have in the case of x equal to 1, if I have x equal to 1, well, guess what? I have 1 plus 4 is 5. 1 minus 1 is 0. Now 5 over 0 will become undefined. And so instead of equaling 0, r of x would be undefined if I have x equal to 1. So that means that for 1, instead of creating an equal to 0 situation, we have a 0 denominator or undefined ratio situation. So 1 will be regarded as not in the domain, NITD, not in the domain. And setting up a table of intervals, just like what we did with the polynomial functions. So between negative 4 and 1, negative 4 is the smaller of the zeros. So we have for the smallest set of values, you have those values which will be less than negative 4. And then for the next, we have those values of x that will be between but not including negative 4 and 1. And then we have, bypassing 1, we have at the upper end, we have those values of x which will be greater than 1. And just laying the groundwork for what we have for the table. So we have the first row we have consisting of the intervals that we will be working around, and then forming rows and partitioning out the subintervals into their own column spaces. All right. So just going at it row by row. So at the top row with the subinterval sections, we're going to be working around and testing out each of the intervals. So just like with the polynomial functions, we'll be putting in a tested value for the input variable x. And now for applying the value, so for the first subinterval, we have values of x less than negative 4, and I can just select any value less than negative 4, and I can just go with, let's say, negative 5. And then between but not including negative 4 and 1, if I go with integers, 0 is a possible choice. And then we have anything greater than 1 we can go with 2. Okay. And okay, so we got the interval sections, and we have tested values, okay, each of which will belong to their respective interval sections that correspond. And after the selection of the input values, again, we're looking at, again, the function that we have for r of x. Okay, so we have r of x. Again, we have equal to x plus 4 all over x minus 1. Okay, and so we have for r of -5. Okay, so if I were to plug in -5 for x, okay, so I would have -5 plus 4 is -1. -5 minus 1, that is going to be a -6. Notice a negative over negative is going to be a positive. So for r of -5, that's going to come out to a positive 1/6. And for what we have in the case of r of 0, so you got 0 plus 4 is 4, 0 minus 1 is -1, and 4 over -1 will go to -4. And for what we have in the case of r of 2, okay, so you got 2 plus 4 is 6, 2 minus 1 is 1, and we have a 6-to-1 ratio, so we have a positive 6. And so just creating the pathway to finding out the solution sets for the respective inequalities we're going to be looking at. Okay, so for the sign of r of x, okay, so for any input that is less than -4, the output is going to be positive. So yeah, the r of x is greater than 0. Then we have next, okay, we're going to have a negative output. So yeah, the r of x is less than 0, and then for any value of x that is greater than 1 selected, the output is going to be positive. All right, now for what we have in the case of the inequalities, again, especially when we get to the equal to statements, okay, we'll be stressing which zeros will be in the domain as well as those that will not. Okay, so -4 is in the domain of this rational expression. 1, on the other hand, is not. Okay, so for what we have in the case of part A in number 60, okay, now the inequality, okay, we have the arrangement in a bit of jumbled order. And so we have x plus 4 over x minus 1. Okay, and this is said to be less than or equal to 0. So we have x plus 4 over x minus 1 is less than or equal to 0. Okay, so we're looking at where we have r of x to be less than or equal to 0. And for what we will have in the case of the solution, okay, now less than or equal to 0, same direction as less than 0. So looking at what we have from the table where r of x is less than 0, and the corresponding interval section can we have involving the limit values of -4 and 1. Okay, and since we have an equal sign there is going to be a potential use for brackets, but not guaranteed. And you can only bracket those zeros that will create an equal to 0 situation, and it'll be with those zeros in the domain. So -4 is in the domain. So we put that in the bracket. And again, since 1 is not in the domain, again, because it would create an undefined ratio as opposed to a ratio that reduces to 0. Okay, so we maintain a parenthesis around 1. And we have for part B, and we have for the ratio, okay, this time we have less than 0. Okay, so we're referencing whereupon, okay, we have R of x is less than 0. And for the solution, because the inequality does not have the equal sign, we're automatically going to have the use of parentheses exclusively. Okay, so where R of x is less than 0, again, we have both -4 and 1 to show up again, and this time we have only using parentheses to surround those values. Now, for what we have in the case of part C, okay, so we have going in the other direction. Okay, so you have x plus 4 over x minus 1 is greater than or equal to 0. So we are referencing where R of x is greater than or equal to 0. Okay, and so we have just using the table, so greater than or equal to 0, same direction as R of x is greater than 0. So we're involving the first and last sets of limits. Okay, the first of which we have -infinity and -4, along with 1 and infinity. And for the enclosures, now again, infinities are boundless. So we have the use of parentheses. And now with the equal sign, okay, we're going to bracket those zeros in the domain. So again, -4 is in the domain, so that is going to be in the bracket. And once again, since 1 is not in the domain, that's going to stay in the parenthesis. Again, for part D, just the remaining inequality. And we already have the results here. Okay, this time where we have R of x is greater than 0. Okay, and the solution is going to be the same numbers involved, but with the exclusive use of parentheses. And again, for greater than 0, again, you have those values of x less than -4, along with those values of x greater than 1. Now, for what we have in the case of the next item, okay, we're looking at a single inequality statement. And for what we have in the case of number 64, okay, we're looking at trying to find out the values of x such that 2 minus x all over x plus 6 is going to be, in this case, greater than or equal to 0. Okay. All right. So looking at what we have for this rational function, again, we can go ahead and get to the zeros. Okay, so you have 2 minus x. If I find the 0 for this, so 2 minus x is equal to 0. I can isolate the x term. And if I do this through the pathway of subtracting 2, so I have -x equal to -2, and changing the signs at both ends, whether multiplying or dividing by -1, we come out to x is equal to 2. 2 minus 2 is equal to 0. And for x plus 6 equal to 0, okay, so you're going to have that x is equal to -6. Okay, and so for what we have, again, just setting the foundation. Okay, so we got our rational function again. With 2 minus x all over x plus 6. And we have with the zeros. Okay, so you got 2, and this comes exclusively from the numerator expression. So 2 is going to be in the domain. And we have -6 to stem from the denominator expression x plus 6. Okay, since we cannot have a 0 denominator in the real number system for a given ratio case, -6 is not in the domain. Okay. And setting up what we have for the table to serve as a pathway to solving this inequality. Okay, so setting up the intervals, and between 2 and -6, okay, we have -6 as the smaller value. So the first interval will be those values of x less than -6. And then we have those values of x between but not including -6 and 2. And then we have, for the remainder, we have those values of x which will be greater than 2. Okay. And again, for what we have in upon establishing the intervals, okay, so once again, after setting up the intervals, okay, again, we can apply test values for the input. Okay, so anything less than -6. Okay, so we're going to have -7 as a possible choice. And we have between -6 and 2. Okay, we can go with 0. And for a value selected to be greater than 2, okay, we can go with the number 3. Okay. Again, we have with r of x. Okay, so again, we have 2 minus x. All over x plus 6. Okay. So for r of -7, okay, so you got like 2 minus -7, so that'll be a +9. -7 plus 6 is -1. And 9 over -1, okay, that is -9. And then we have for r of 0, okay, so you got 2 minus 0 is 2. 0 plus 6 is 6. And 2/6 reduces to 1/3. And for r of 3, okay, so you got 2 minus 3 is -1. And 3 plus 6 is 9. Okay, so that is already reduced. So we have -1/9. And for the sign of r of x, okay, so first section, okay, we have a negative. So we had the r of x is less than 0. Next, okay, we have a positive. So we have the r of x is greater than 0, and we have, with the last, we have a negative. So we have that r of x is less than 0, okay. And going back to our inequality, okay, which we had at 2 minus x over x plus 6 is greater than or equal to 0. Okay. And again, so 2 minus x over x plus 6, okay, that is already baked in as the function r of x. And looking at the solution set of x in interval notation. Okay, so r of x is greater than or equal to 0. Okay, this will be in the same direction as r of x is greater than 0. So we have this in this middle interval section. So we are involving the numbers -6 and 2. And if I had just greater than 0, both the values would be in parentheses, but with the equal sign, again, there is the possible use of a bracket. And so we got 2 is in the domain. And we have -6 is not in the domain. So -6 not being in the domain. So that's still going to be in the parentheses, but with 2 in the domain. Okay, that creates the equal to 0 part. And that value is going to be bracketed. And that will be the interval solution for what we have in the case of problem 64. All right. Now for number 80, okay, we have a bit of an added dynamic, okay, thrown in, and we have what will be referred to as comparison inequalities between rational expressions. And for what we have in the case of number 80, okay, so we have this expression in terms of the variable z. And here we have 2 over z minus 1 is greater than -4 over z. Okay. Now let's say that if okay, so you have a comparison of ratios. You do not see 0 right yet. Okay, and if I write this inequality in terms of comparing to 0, okay, so to have 0 on the right hand side, I can just move this rational expression over by adding. Okay, so you got 2 over z minus 1 and we have plus 4 over z is greater than 0. Now, this is where it gets a little bit tricky because we're going to consolidate into a single ratio, kind of going back to the methods used, okay, back in chapter R. So for what we have in the case of 2 over z minus 1, we have plus 4 over z. Okay, and if I'm looking at combining, okay, now for the ratios, okay, now we're going to put in terms of the least common denominator, which in this case is going to be z times the quantity of z minus 1 so right now we got 2 over z minus 1. And we're going to multiply by 1 in the form of the missing factor over itself. So that's going to be z over z. plus 4 over z, and that's going to be multiplied by 1 in the form of the other factor over itself. So I have z minus 1 all over itself. And looking at putting together what we have. Okay, so we got 2 times z. And we have plus, and we have 4 all over z minus 1. So we've got 2z, and what's going to be plus 4z minus 4. And we have all over z times the quantity of z minus 1. And finally putting all together. Okay, so we got 6z minus 4 all over z times the quantity of z minus 1. Okay, so in the rewrites, okay, so establishing as a comparison to 0 inequality, so I added 4 over z, and then combining as a single ratio, that's going to establish what we have for the rational function we're going to build a table around. Okay, so we got 6z minus 4 all over z times the quantity of z minus 1 is greater than 0. Okay. So for what we have, okay, so for the ratio, okay, so we have r of z. Okay, so you have z equal to 6z minus 4 all over z times the quantity of z minus 1. And just looking at establishing the zeros. So if I have, so we've got 3 z expressions, okay, and we have with the numerator. So we have 6z minus 4, and if I set this equal to 0, so we have 6z is equal to 4, and division by 6, okay, is going to yield 4 over 6, and 4/6 is reducible to 2/3. And we have with the other factors, okay, we have from z, I have z is equal to 0, and for z minus 1, if that is equal to 0, so we have that z is equal to 1, okay, and so for this rational expression, okay, we're going to have 3 zeros. And again, 2/3, which we have to come from 6z minus 4, the numerator. Okay, now that one is going to be in the domain. And 0 stems from the z factor in the denominator. So that one is not in the domain. And from z minus 1, okay, we have z equal to 1. And since z minus 1 is in the denominator, 1 is not in the domain either. Okay, and so establishing what we have working around r of z. Okay, so you have with the first interval section, okay, now these values can be squeezed rather squeezed tightly together. Okay, and we have okay, so for 2/3, 0, and 1, okay, we'll have smallest of the zeros is going to be 0 itself. So the first interval section will be those values of z less than 0, and then we have those values of z greater than 0 and less than 2/3. And then we have those values of z greater than 2/3 and less than 1. And we have for the remainder, we have those values of z greater than 1. Okay, and just separating the interval sections into their own column spaces. And column headings for that matter. All right, so we have for the first round, okay, so this time we're looking at test values for z, okay, and we have for anything that is less than 0, we can go with -1. Now, the thing about the next two intervals is that we cannot fit an integer between the limits. So between 0 and 2/3, I can just go with the fraction, we'll say 1/3. And between 2/3 and 1, okay, like 2/3 is like 0.67, and 1, it could be a fraction like 4/5, or it could be a decimal. I'm just going to go with 0.7. And we have for anything greater than 1, okay, we can go with the number 2. Okay, now we have with the function r of z. Again, this is, once again, the consolidated ratio, so it has 6z minus 4. I had all over z times the quantity of z minus 1. Okay, now for the function values, okay, the important thing is not so much the exactness of the value as it is the sign value. Okay, and for -1, okay, now, okay, so for -1, okay, I have like 6 times -1 minus 4 is -10, and then I have -1 times -2 is a positive 2, so you have like -10 over 2, and that is going to become -5. Now for r of 1/3, okay, that's going to come out to a positive result. And in fact, for this one, okay, so you have like, in this case, that's going to come out to a positive 9. And for r of 0.7, okay, it's going to come out to a negative non-integer, so you have -20 over 21. And for r of 2, okay, that would reduce to a positive 4. Okay. And again, the importance is not so much with the exact value of the output as it is the sign value. You want to have at least the sign value correct. Or the sign correct. Okay, so we got for the sign of r of z, okay, And we have for the first any value selected that is less than 0. The output is negative. So we have the R of Z is less than 0. Next, okay, we have a positive. Whereupon we have R of Z is greater than 0. Next, we have another negative. Whereupon we have the R of Z is less than 0. And the last, we have a positive, where R of Z is greater than 0. Okay, so bringing it all back. So we started out with 2 over Z minus 1 is greater than negative 4 over Z and again having put together as a comparison to 0 ratio and consolidating the terms. Okay, so I had 6Z minus 4 all over Z times the quantity of Z minus 1 and that's going to be where that is greater than 0. And so we're looking at where R of Z is greater than 0. And so for what we have in the case of the solution set, notice that there is not an equal sign, so we're going to have the exclusive use of parentheses. Okay, so where we have R of Z greater than 0, okay, that's going to be with the second and the last subinterval sections. And that's going to be the outcome in this particular case. All right, now, and let's say, let's give a hypothetical. I think I can duplicate this. Now let's say that if our inequality had the equal sign involved, this is where stressing the zeros in the domain as well as not in the domain will be a concern. Okay, so again, we have 2/3 is in the domain, whereas the 0 and 1 are not in the domain. And for the solution set, if I had the greater than or equal to as opposed to just greater than. Okay, so you have for 0 to 2/3, 0 is not in the domain, 2/3 is. So you have a parenthesis around 0, 2/3 being in the domain, so that would be in the bracket. And we have 1 is not in the domain. So that's going to be in the parenthesis, and already infinities are boundless, and that's also going to be in the parenthesis. Okay, and so if our statement had the equal sign, that would be our interval solution. All right, now just looking at other cases involving inequalities, and from your test 3 review set, and since we're kind of just into the comparison inequalities, I'll tell you what, if we have, let's say, for numbers 18 and 19. Okay, for rational inequalities. Okay, so for 18, we're looking at where we have x plus 4 over x minus 7 is less than or equal to 0. Again, it says here to solve and write the response using interval notation. Okay, so again, we have with this ratio. So if I were to attain the zeros of the x expressions, okay, so if I have x plus 4 equal to 0, we have x is equal to negative 4, and the other expression, okay, we have in the denominator with x minus 7, and if that is equal to 0, we're going to have the x is equal to 7. Okay, so once again, establishing things. Okay, so we already have our inequality expressed in terms of less than or equal to 0. So we say our rational expression, we have r of x is equal to x plus 4 all over x minus 7. And for what we have in the case of the zeros, okay, so negative 4 stems from the numerator, x plus 4, so that is in the domain. And we have with the other 0, 7, that's going to create a 0 denominator. And so that one is not in the domain. Okay. All right. So we have r of x established and the zeros determined. And for the interval sections, okay, so we got those values of x, okay, less than negative 4. And then we have those values of x greater than negative 4 and less than 7. And finally, we have those values of x greater than 7. I'm just going to go ahead and lay out the row and the column headings before doing the partitioning. Okay, so I have these three interval sections. Okay, and looking at supplying tested values for the input. Okay, so we're looking at, for the first one, okay, we're looking at selecting a value of x that is less than negative 4, and the next we have those values upon which we can select must come from those that are greater than negative 4 and less than 7, and then we have for the remainder, okay, we have that value selected must be greater than 7. Okay, so looking at what we have here, so anything less than negative 4, we can go with negative 5. And between negative 4 and 7, 0 is an option. Anything greater than 7, we can go with the number 8. All right, so for the selected input values. Okay, so the outputs, okay, we have first of all r of -5. And so we have -5 plus 4, that is -1. -5 minus 7 is -12. And that's going to be a positive 1/12. And for r of 0, okay, so you have 0 plus 4 over 0 minus 7. And that's going to be automatically -4/7. And for what we have in the case of r of 8, okay, so you have 8 plus 4 is 12, 8 minus 7 is 1, so you have a positive 12-to-1 ratio. And for the sign values of r of x, okay, so anything selected for the input that is less than -4, we have a positive output. So you have r of x is greater than 0, and then we have anything greater than -4 and less than 7. And we'll have a negative output, so we have r of x is less than 0, and then for anything greater than 7, we have a positive output, so we have r of x is greater than 0. Okay, so going back to our inequality, so you have x plus 4 over x minus 7 is less than or equal to 0. Again, that's going to be referencing r of x is less than or equal to 0. And for what we have in the case of the solution, so we have r of x to be at least less than 0, same direction. We're involving the limit values, -4 and 7. And in terms of the enclosure, now -4 is in the domain, so that creates the equal to 0 part, so we can put -4 in the bracket. But since 7 creates a 0 denominator, it is not in the domain, and that value is going to remain in the parentheses. Okay, so that would be your interval solution for what we have in number 18. All right, now where we have a comparison inequality, now for number 19, okay, we have x plus 8 all over x minus 1 is greater than or equal to -2. And it says to write your answer as an interval or a union of intervals. Okay, so we have, in the case of number 19, okay, so you have a comparison inequality. And if I rewrite this in terms of a comparison to 0 inequality, so what I can do here is I can add 2. And so we'll have in the rewrite, so we have x plus 8 over x minus 1 plus 2 is greater than or equal to 0. And just like what I did with two ratios, I'm going to add these terms together and consolidate. Okay. Okay, so you have x plus 8 over x minus 1 plus 2. You can also write that as 2 over 1. And least common denominator is going to be x minus 1 And the first ratio we already have expressed in terms of the least common denominator, since that is the fraction from which we have the LCD to originate. Now for 2, or 2 over 1, to rewrite in terms of the least common denominator, I'm going to multiply 2 by 1 in the form of x minus 1 over itself. So you got x plus 8, and we have plus 2 times the quantity of x minus 1. So you have x plus 8, and you got plus 2x minus 2. All over x minus 1. And so just putting together, okay, so you got 3x plus 6 over x minus 1. And this is optional, but I'm going to go ahead and write this in factored form. So 3x plus 6, that'll be 3 times the quantity of x plus 2 all over x minus 1. Okay, so for what we have in establishing as a single ratio in comparison to 0 inequality, okay, so for x plus 8 over x minus 1 plus 2, so we have, again, so you have 3 times the quantity of x plus 2 over x minus 1 is greater than or equal to 0. Okay, so just looking at what we have in the setup. Okay, so again, we have for r of x, yeah, 3 times the quantity of x plus 2 all over x minus 1, and looking at establishing the zeros. Okay, so for our 0 terms, if x plus 2 is equal to 0, we have that x is equal to negative 2 in the denominator. Okay, so you have x minus 1 equals 0, and we have that x is equal to 1. So for this ratio, so for r of x, okay, we have for the zeros, we have negative 2, and since this stems from x plus 2 in the numerator, negative 2 is in the domain, and since 1 stems from the denominator expression x minus 1, one is not in the domain. Okay, and so setting up our table. Okay, so you got for the interval. Okay, so the lesser of the zeros we have at negative 2. So the first interval will be those values of x less than negative 2. And next we have those values of x greater than negative 2 and less than 1. And for the remainder we have those values of x which will be greater than 1. and looking at establishing test values throughout. Okay, so if I select any value that is less than -2, and go with -3. And between -2 and 1, okay, we can fit in 0. Anything greater than 1, we can go with the number 2. Okay. So looking at what we have here for the value of the rational function. Okay, so for r of -3, okay, so you have 3 times, okay, -3 plus 2 is -1. 3 times -1 is -3. And we have -3 minus 1 is a -4. So you got -3 over -4. And a negative over a negative becomes a positive. And for r of 0, so you got 3 times 2 is 6. 0 minus 1 is -1. And 6 over -1, so that will go to -6. And for r of 2, okay, so you got 2 minus 1 is 1. And 2 plus 2 is 4. 3 times 4 is 12. And 12 over 1 goes to positive 12. And for the sign of r of x, so you got a positive. So you have r of x is greater than 0. Next we have a negative, whereupon we have r of x is less than 0. Then we have a positive. Again, where we're going to have r of x is greater than 0. Okay, so just going back to what we have with our original inequality. So you have x plus 8 over x minus 1. Is greater than or equal to -2. And once I consolidate it as a single ratio compared to 0, so this had come down to 3 times the quantity of x plus 2 all over x minus 1 is greater than or equal to 0. And again, that is referencing where we have r of x is greater than or equal to 0. And for what we have in the case of the solution, okay, so we have where r of x is greater than or equal to 0, so I can reference where we have r of x to be greater than 0. So I'm looking at involving the limit values, -infinity and -2, along with 1 and infinity. And for grouping, okay, so infinities are boundless, so I still have parentheses. Okay, now for what I have in the case of -2, again, so -2 is in the domain, 1 is not. And so between the values, okay, the creation of the equal to 0 part or the equal part period, that's going to stem only from -2. So -2 is going to be in the bracket. And again, 1 is going to create the undefined ratio in contrast to the equal to 0. So 1 is going to be in the parenthesis. And so that'll be the resulting interval solution for what we have here. All right. And if you notice now, so far we've had alternating sign changes like positive, negative throughout. And one might wonder, okay, if that's going to be always the case. And right now, this is what we have dealt with so far. And so if we look at what we have with some of our other inequalities, okay, and and we have, like in the case of number 15. Okay, so I have, just going back to polynomial inequalities. Now we have x squared minus 2x is said to be greater than or equal to 8. And if I take what I have here and write in terms of comparing to 0, so I can just move the 8 over. Okay, so I have x squared minus 2x minus 8 is greater than or equal to 0. And so that's going to be our f of x is greater than or equal to 0. Okay, and looking at what we have for f of x. We have x squared minus 2x minus 8. Okay, so this would be the function we'll be working around in the table setup, and also looking for the zeros. And we have for x squared minus 2x minus 8 is equal to 0. And if I factor, so I have the quantity of x minus 4 times that of x plus 2 is equal to 0. And itemizing the factors and setting equal to 0. Okay, so you have x minus 4 is equal to 0, as well as x plus 2 is equal to 0. If x minus 4 is equal to 0, so you have that x is equal to 4, for x plus 2 equal to 0. Okay, so I have that x is equal to -2. Okay, so again, just looking at what we have here. So this is our polynomial function, and we have, along with this, okay, we have our zeros. You got 4 and -2, and to make the arrangement kind of a bit more of a user-friendly segue to the table, I can just arrange in increasing order. So I have the zeros at -2 and 4. So I have among the intervals. Okay, so -2 is the lesser of the zeros. Okay, yeah, the first interval will be those values of x less than -2. And then I have those values of x greater than -2 and less than 4. And I finally have those values of x greater than 4. Okay, and in terms of the tested values, okay, so anything less than -2, negative 3 would fit the bill. Between negative 2 and 4, I can also reapply 0. Anything greater than 4, I can go with the number 5. Okay, now working with the input values. Okay, so we got for f of negative 3. Okay, so we got negative 3 squared minus 2 times negative 3 minus 8. Square root of negative 3 is 9. Negative 2 times negative 3 is plus 6, which is 15 minus 8. Okay, and so this will come out to a positive 7. And for what we have in the case of f of 0, okay, 0 squared is 0, negative 2 times 0 is 0. So the only non-negligible constant we have is minus 8. So we have f of 0 equal to minus 8. And we have finally for f of 5. Okay, so you have 5 squared, which will be 25. Negative 2 times 5, which is negative 10. And we have followed by the subtraction of 8, so you got 25. Minus 10 is 15 minus 8, and that also lands at positive 7. And for the sign of f of x, okay, so you have a positive. So you have f of x is greater than 0. Then next we have for negative 8, okay, we'll have f of x to be less than 0. So you got negative, and then finally we have positive. Where we have that f of x is greater than 0. Okay, so bringing it all back. Okay, so we started out with x squared minus 2x is greater than or equal to 8, which carried over to x squared minus 2x minus 8 is greater than or equal to 0. And this will be bringing forth the issue, okay, of determining where f of x is greater than or equal to 0. Okay, and so we're going to have, in the case of the solution, and again, we have in the direction of where f of x is greater than 0. So you're looking at the first and the last subinterval sections. Okay. And for polynomial functions, these zeros are already in the domain. And infinities are boundless, so you have parentheses still. But with negative 2 and 4, those create the equal to 0 part. and those are included in the solution. So both -2 and 4 will be bracketed, and that will be your interval solution for what we have for this inequality that we have in number 15. All right, now for what we have in the case of number 16, okay, so we just got, let's go, I'm going to write this. Okay, so you got x plus 2 times x minus 4 times the quantity of 6 is greater than 0. There we go. Okay, so we have for number 16, okay, we kind of have established, okay, what our f of x is. Okay, and since we already have the factored form, we'll go ahead and identify the zeros. Okay, so you got with the zeros, from x plus 2, I have -2. From x minus 4, I have 4. From x plus 6, I have -6. And just in the creation of the interval sections, remember, okay, you want to put the arrangement where the zeros are in increasing order. Okay, so we have in the set, okay, so the least of the zeros we have at -6. So the first interval will be for those values of x less than -6. Then you have followed by those values of x greater than -6 and less than -2. And we have those values of x greater than -2 and less than 4. Finally, we have those values of x greater than 4. Okay, and just for the test value x, okay, so anything less than -6, -7 is a possibility. Between -6 and -2, we can go with -3. Between -2 and 4, we have 0, which will fit. Anything greater than 4, again, we can go with the number 5. There we go. Okay, so we have with our function, okay, so if I plug in -7 for x, okay, so for f of -7, Negative 7 plus 2 is negative 5. Negative 7 minus 4 is negative 11. Negative 7 plus 6 is negative 1. And for the result, okay, we're going to have a negative 55. Now for f of negative 3, we got negative 3 plus 2 is negative 1. Negative 3 minus 4 is negative 7. Negative 3 plus 6 is going to be a positive 3. So we have for that output, okay, that is going to be 7 times 3. So that's going to be positive 21. And for f of 0, okay, so you got 0 plus 2 is 2. 0 minus 4 is negative 4. And 0 plus 6 is 6. 2 times negative 4 is negative 8 times 6. So we have negative 48. And for f of 5, okay, so you got 5 plus 2 is 7. 5 minus 4 is 1. 5 plus 6 is 11. 7 times 1 is 7. 7 times 11. So that's going to come out to a positive 77. And for the sign of f of x, okay, any value less than negative 6 selected for the input, the output is going to be negative. So we have f of x is less than 0. For the next section, we have a positive output. So the f of x is greater than 0. Next, we have negative output. And the last case, we have a positive output. So we have that f of x is greater than 0. And so just looking at what we have, going back to our original inequality statement. Okay, that was said to be greater than 0. And with f of x as the product of these three binomials, okay. So now we're referencing where f of x is greater than 0. So there's no equal sign, so we're going to have the exclusive use of parentheses if we have interval solutions. And looking at where we have f of x is greater than 0. So this will be with the second and the last interval sections. And the first will be those values of x such that negative 6 is less than x is less than negative 2. The other part will be where we have all values of x greater than 4. Okay. And so far we have had alternating positives and negatives. Okay. And the question I brought up earlier was that, is that always going to be the case? Well, I saved number 17 for the last of the inequalities to deal with. And there's going to be like a twofold situation with this type of problem. I'm going to bring up not only where we have the statement to be less than 0, but also where it is less than or equal to 0. And And for what we have in the case of number 17, just going to okay, so you got the square of x plus 4 times the quantity of x minus 6, okay, is less than 0. Okay, now we already have the expression or the inequality laid out in comparison to 0 terms. Now let's go ahead and mention the zeros. Okay, so we have this function is already presented in factored form. So we can go ahead and get to the zeros. So from x plus 4, we have the x is equal to negative 4. From x minus 6, okay, we have the x is equal to 6. Okay, and looking at the intervals, okay, so we have negative 4 is the smaller of the zeros. So the first interval we'll be working around, we have those values of x less than negative 4, followed by those values of x between but not including negative 4 and 6. And finally, we had those values of x greater than 6. Again, we have test value for the input. Again, working with the function for each input. Again, so you have f of x is equal to the square of x plus 4 times the quantity of x minus 6. Okay, so we have with the intervals. Okay, so for test value inputs, anything less than negative 4, we have negative 5 is a choice. Between negative 4 and 6, we have 0. And anything greater than 6, we'll say 7. And for what we have in the case of the function values, okay, so you have with f of negative 5, f of 0, and f of 7. Okay, so with negative 5, you got negative 5 plus 4 is negative 1, but the square of negative 1 is a positive 1. Negative 5 minus 6 is negative 11, and 1 times negative 11 is a minus 11. For 0, we got 0 plus 4 is 4. 4 squared is 16. 0 minus 6 is negative 6. 16 times negative 6 is a negative 96. For f of 7, 7 plus 4 is 11. The square of 11 is 121. 7 minus 6 is 1. And 121 times 1 is still 121. Okay, now for the sign of f of x, okay, anything less than negative 4 selected for the input, the output is negative. So we have that f of x is less than 0. And notice, okay, the next, okay, now we've been on a pattern now, like negative leads to a positive, which leads to a negative, which leads to a positive. But guess what? This is like our first case where we have the same sign in consecutive interval sections, because here, anything greater than -4 and less than 6 for the input leads to a negative output. So we have, again, f of x is less than 0. And then we have, for any input greater than 6 that is selected, the output is going to be positive. So we have that f of x is greater than 0. So we have with our inequality, so again we have the square of x plus 4 times the quantity of x minus 6. And again, the problem was where we had to be less than 0. Okay, and with f of x as the square of x plus 4 times the quantity of x minus 6 is less than 0. So we're looking at where we have f of x to be less than 0. And for the solution, okay, so locating where f of x is less than 0. So you have these back-to-back interval sections. There's no equal sign, so we're going to maintain the use of parentheses throughout. So your solution set will be where we have the values of x less than -4, along with those values of x such that -4 is less than x is less than 6. Okay, so that is going to be the answer here. But I'm just going to bring up something. I don't think Alex will bring this up. In fact, the nature of this would be where you would have something like maybe in calculus. But if you happen to have the equal sign included, if this happened to be the problem, not less than 0, but less than or equal to 0, if we have f of x is less than or equal to 0. Now, what you're going to be looking at, still, you have less than or equal to 0, same direction as where we have f of x is less than 0. And with the equal to 0 part, again, your zeros that would cause this polynomial to be equal to 0 will be -4 and 6. And with the inclusion of the equal sign, -4 and 6 would be part of the solution. So you would have -4 and 6 in alignment with what we have looked at so far. Those would be bracketed. But now there is an added dimension here. And what that is, if you notice, okay, you have values less than or equal to -4, and then you have -4 is less, or I should say -4 is less than or equal to x is less than or equal to 6. Notice we have in the middle. we have, at the upper end, we have x equal to -4, and for the second half, we have x equal to -4. And you say that the sections are united. By x equal to -4. So for what you would have in the case of the solution, okay, since you have both of these sections united by x equal to -4, so these end pieces will become consolidated. So instead of two separate interval sections, you're going to wind up having pieced together everything from -infinity and running through -4, since x equals -4 bridges the gap. And so your solution is going to be all values of x such that x is less than or equal to +6. And that is if the nature of the inequality had the equal sign. So that would be your solution in this case.